Hi, dear students. I'm Dr. Siva here. Today, in this lecture, we will discuss about alternative to transistor technology as well as um, what is a Kane model, which has been a accepted model for this new technology, which is called quantum computing. Okay. We explore alternative to transistor-based computing technologies, which is focusing particularly on quantum computing and the Kane model. As transistor scaling approaches, atomic dimensions, classical physics becomes insufficient, and quantum-based approaches become sequential. This presentation connects quantum mechanics, solid-state physics, and computational architecture. Alternative to transistor technology, quantum computing. In this slide, we'll introduce the idea that the next major shift in computing is quantum computing. Although it is fundamentally different from today's classical computing, it still falls under nanocomputing because it exploits properties of single atoms and subatomic behavior. This means computation is no longer based on electron flow in semiconductor channels, but instead on quantum states of matter. This marks a paradigm shift, not just a technological upgrade. Quantum mechanics versus classical mechanics will be discussed here. We have studied already, but however, this slide explains again the classical computers operate on binary value 0 and 1, which is determined by the presence or absence of the current. Quantum computing replaces with the qubit. Bits are being replaced by qubits. Here, the values 0 and 1 correspond to atomic energy, states resting or excited. However, quantum mechanics allows atoms to exit. They are actually existing at in both the states, so we call it in a coherent superposition, meaning the atom can simultaneously represent both 0 and 1 with equal probability. This concept has no classical equivalent and is fun, and it is actually the foundational to quantum information science. This is the model for quantum computing architecture. In this slide, we see a conceptual model of a quantum computing architecture. Unlike classical circuits, which are actually made up of transistors and metal interconnections, these quantum computers require precise placement of atoms or qubit structures. The design must support qubit initialization, manipulation, coupling, readout, uh, while we are actually preventing the decoherence. Again, the design must support qubit initialization, manipulation, coupling, and readout. So, meanwhile, we are actually preventing the decoherence. This slide serves as a bridging between a Kane model, one of the earliest solid state quantum computing proposal. Okay, Kane model, which is actually the phosphorus donor based atoms. Donors will be actually in a silicon substrate. Okay, here you can actually see where the phosphorus donor atoms are embedded isotopically on a purified silicon. These donors are placed 20 nanometer apart from each other and 20 nanometer below the surface with an insulating oxide layer above them. Metal A gates and J gates are positioned to control the atoms. Phosphorus 31 has a nuclear spin of 1 by 2, while silicon 28 has 0 spin state, which is actually having spin 0. Silicon having spin 0, phosphorus is actually having 1 by 2. Which makes the environment, these are all actually like silicon is actually making the environment extremely stable for the nuclear spin of 1 by 2 of phosphorus atom. Okay. So using nuclear spinors qubits, which provides extremely long decoherence times on the order of 10 to the power 18 seconds at a millikelvin temperature. Again, the decoherence time is 10 to the power 18 seconds here, which is crucial for reliable quantum computation. Manipulation is actually achieved using oscillating magnetic fields, similar to nuclear magnetic resonance, by adding adjacent A gate voltages. Individual qubits can be spectrally addressed via Larmor frequency tuning. These details related to the architectures are being provided here in this slide. Okay. So now how this interaction is actually happening and how we read out from the Kane model. This is a final slide which explains how qubit interact and how computation results are actually read. Nuclear spins do not naturally interact over 20 nanometer distances. So electron spins are used as mediators. Electron spins are actually being used as the mediators. Under control of A gate, nuclear spin information is transferred to the donor electron. Then the J gate voltage brings adjacent electrons into shared region where their spins interact, enabling two qubit operations such as an entanglement. For read out operation, Kane proposed spin dependent tunneling where an electric field forces an electron to tunnel to form a D plus donor donor minus pair. This results this actually resulting a charge imbalance is actually will be produced. This will be actually producing a charge imbalance which is detected using a single electron transistor. The creation of the D plus and the D minus will create a charge imbalance which will be actually measured by the single electron transistor. However, this method faces two challenges. The first one is the D state, D negative state couples strongly to the environment, which can cause the rapid decoherence, and its lifetime may be too short for reliable measurement to tunneling into the conduction band. These challenges illustrate why quantum hardware engineering remains demanding today. With this, we can actually stop this lecture and we will actually continue from the next topic in the next lecture. Thank you, students.